Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
You know, when you look up at the night sky, it's really easy to just assume the universe is this fully understood static place.
Right, yeah. It feels permanent, like it's always just been that way.
Exactly. Like what you see is what you get. But it's really not. We are looking at a recent cosmic curveball today that, well, it honestly made scientists think our entire understanding of cosmology was completely broken.
It was a very real panic. And to understand why, we're going to explore a very specific tiny anomaly. It's called G-Limp-Ser 17775. It's one of the so-called little red dots.
Right.
And we're going to reconstruct how astronomers are essentially putting together this massively complex puzzle that spans billions of light years, combining data from the most powerful telescopes ever built to solve this fundamental mystery.
Okay, let's unpack this, because the scale here is really old. We're talking about objects that emerged just like 600 million years after the Big Bang, which initially seemed utterly impossible.
Yeah, but sometimes it's the smallest anomalies in astronomy that force us to completely rethink the fundamental building blocks of, well, galaxies and black holes.
So take us back to 2022. NASA's James Webb Space Telescope finally turns on, right?
Exactly. It gets out to its orbit, unfolds those golden mirrors, begins science operations, and basically immediately starts seeing things that shouldn't be there.
Because the goal was to look back to the cosmic dawn,
Right.
to see those very first, fragile little galaxies forming from gas.
Right. But the data coming back didn't show fragile forming galaxies. It showed these mysterious red objects that were incredibly bright, sitting right there in the absolute infancy of the universe, just 600 million years in.
I mean, if you compress the entire 13.8 billion year history of the universe into a single calendar year, 600 million years is like mid-January. It's the absolute beginning.
It is. And it caused a total panic. Because in our standard cosmological models, galaxy formation is a hierarchical, tedious process. You start with dark matter pooling together.
Right.
And those dark matter halos exert gravity to slowly pull in normal matter, like hydrogen and helium gas. And that gas has to cool, collapse, ignite into the first stars.
And then undergo countless chaotic mergers over billions of years.
Exactly. It's not a quick process. So finding these incredibly bright objects so early completely defied the established timeline.
I mean, we've compared this to walking into a kindergarten classroom expecting to see 5-year-olds playing with wooden blocks. But instead, you find a room full of toddlers with full beards, smoking pipes, and holding PhDs in astrophysics.
That is exactly what it felt like to the community. And this raises an important question, right? If the timeline of the universe is wrong, then our fundamental physics models need rewriting. We needed a perfect test subject to figure out what was really generating this light.
Because you can't just dismantle the entire framework of modern physics without being absolutely certain you aren't just misreading the data.
Right. The initial fear of broken cosmology came from early broad data. Some researchers were baffled by how galaxies could have grown so incredibly massive so fast, assuming all this light was coming from billions of early stars.
But studying something that distant and faint is, it's pushing the absolute limits of our technology.
It is. You need an enormous amount of uninterrupted observation time. Which brings us to the lucky break we got with G-Limp 17775.
Yes, the magnificent accident. This involves a team led by Vasily Kokorev at the University of Texas at Austin, right?
That's right. And what's funny is they weren't even originally looking to solve the little red dot mystery.
Wait, really?
Yeah. Their primary target was a specific galaxy cluster called Abell S2063. They were hunting for population thirst stars and faint galaxies within and behind that cluster.
Okay, hold on. Population 3 stars. Those are the very first generation of stars to ever ignite in the universe, right? Made of pure, pristine hydrogen and helium.
Exactly, the theoretical holy grail. So they were surveying this massive galaxy cluster, hoping to spot them. But while they were looking, their data captured something else far in the background.
The unassuming little red dot, G-Limp 17775.
Right. Now, this object sits at a cosmological redshift of 3.5. So we are seeing it as existed roughly 1.8 billion years after the Big Bang.
But the age isn't even the most important part here. It's the geography.
Absolutely. It happened to be located directly behind the massive galaxy cluster Abell S1063. And because of that precise alignment, the immense gravity of the cluster actually bent and magnified the light of the little red dot.
Wait, so we essentially used an entire galaxy cluster as a pair of reading glasses.
That is exactly what we did. It's a phenomenon called gravitational lensing. The cluster acts as nature's magnifying glass.
That is just incredible, the scale of using the universe's own gravity to upgrade our technology.
It really is.
Yeah.
Practically speaking, the James Webb Space Telescope spent about 30 hours collecting a spectrum of this dot. But because of the gravitational lensing, it was the equivalent of 80 hours of telescope time.
Wow.
Yeah. That fortunate set of circumstances yielded the deepest, most detailed spectrum of a little red dot ever captured. It turned a faint smudge into a highly readable data set.
So they secure this unprecedented 80-hour equivalent data set, but having the data isn't the same as understanding it. I know Kokarov made a comment like, when we saw the spectrum for the first time, it was like having all the pieces of a puzzle scattered on the floor.
It's an accurate sentiment because they aren't looking at a photograph, they're looking at a spectrum.
Right, which is basically breaking the light down into its chemical fingerprint.
Exactly. A spectral line corresponds to specific elements absorbing and emitting light. And the Webb data revealed more than 40 distinct spectral lines from this tiny red source.
That's a lot of puzzle pieces to sort out.
It is. They found common elements you'd expect, like hydrogen, oxygen, and helium. But the surprise wasn't finding those elements. It was how those elements were behaving.
Here's where it gets really interesting, I think, because at first, a few pieces look like nothing, but once combined, a weird image started to form.
Right, because the spectral lines did not fit the simple expected model of a rotating gas cloud. If this were a normal, fast-growing galaxy full of stars, the lines would look like relatively neat bell curves.
But these lines were totally distorted, right?
They were chaotic,
Yeah.
massively distorted. And that tells us that whatever's distorting these elements is not a normal rotating cloud of gas. The answer actually lies in two specific extreme anomalies in the data.
Okay, let's break those down. First is what's called electron scattering, and second is the iron forest.
Yes. Let's start with the electron scattering, which causes a broadening effect in the spectral lines. What's fascinating here is that this is a telltale signature of a dense, layered gas cocoon enshrouding the source.
So the light is physically fighting its way through a thick fog of gas.
Specifically, an incredibly dense, highly ionized plasma thick with free-floating electrons. When a photon collides with a free electron, it scatters. It loses a bit of energy and changes direction.
And that smears the spectral line out across the graph. Okay, so that's the dense cocoon. But what about the iron forest?
The team discovered 16 specific iron lines in the data, along with specific oxygen line ratios. Now, creating these specific lines requires an incredibly high energy source.
Because you have to rip multiple electrons away from the iron atoms, right? Which takes unimaginable heat.
Exactly. A normal cluster of stars, even billions of them, cannot produce that kind of sustained high-energy environment.
It's basically like hearing a muffled, booming roar from behind a heavy, fireproof theater curtain. The curtain is that dense cocoon of gas causing the scattering.
Right.
You notice the curtain is glowing hot with signatures of vaporized metal, the iron forest. You know, instantly there's a massive furnace behind it, not just a campfire.
That's a perfect analogy. And there was a third indicator involving helium. Both the fluorescence and absorption of helium were present in the data.
What does that tell us?
Individually, they proved there is a dense medium enveloping a really powerful central engine. So all these strange signatures, the dense cocoon, the immense heat, the muffled energy, they all converge on one specific theoretical model.
The black hole star, which honestly sounds like an oxymoron.
I know. The name is a bit poetic. But the BH star scenario interprets JILIMPS 17775 as a rapidly accreting or growing supermassive black hole enveloped in a dense cocoon of partially ionized gas.
Okay, but how does a black hole act like a star? I mean, black holes absorb light.
It's the accretion disk. As the black hole feeds, the material spiraling into it heats up to millions of degrees, pumping out extreme ultraviolet light and X-rays.
So that's the blast furnace inside our theater curtain.
Exactly. But that intense light can't escape directly. It slams into the dense gas cocoon surrounding the black hole. The cocoon reprocesses that intense light and emits it as harmless, warm red light.
That is wild. It's laundering the energy. But wait, this solves a massive mystery, right? Because most of these little red dots are oddly faint in X-rays.
Yes, which usually gives away the presence of a supermassive black hole. If it's a black hole, it should be screaming in X-rays.
So why aren't we seeing them?
The BH star model perfectly accounts for this. The dense gas cocoon is acting like a lead vest. It's physically opaque to X-rays, absorbing those emissions before they can ever escape into space.
So what does this all mean for you listening? We are basically looking at a black hole hiding in a fog bank of its own making, eating material so fast that it lights up the fog from the inside.
That's exactly it. The model fit the data beautifully. But, as with all science, there was one nagging discrepancy. One piece of the puzzle was missing from the Glimpse 187775 data.
Right, the Balmer break. Let's talk about that. What is a Balmer break for anyone not staring at astronomical charts every day?
The Balmer break is a strong dip in emitted light at a very specific wavelength. It's typically a signature characteristic of these little red dots. It happens when hydrogen gas absorbs a specific energy of light.
But in this specific object, Glimpse 17775, this dip was unusually weak.
It was. It was just a shallow dip instead of a sharp cliff. And to solve this, the UT Austin team couldn't just rely on Webb anymore. Webb's infrared data had been pushed as far as it could go.
So they needed a different perspective. They brought in ancillary data from the Hubble Space Telescope, right?
Yes, specifically deep archival data from the Frontier Fields and Buffalo observing programs. Hubble operates in the visible and ultraviolet parts of the spectrum.
And when they combined the Hubble data with the Webb data, the mystery was solved.
It was a revelation. The combined data showed that Glimpse 17775 is actually surrounded by a giant host galaxy.
Oh, wow. So it's not just floating out there alone.
No. And the stars in this massive host galaxy are incredibly young and hot, producing an excess of bright blue light.
Which completely explains the weak Balmer break. Because it's like trying to hear a sudden moment of silence in an orchestral performance. That silence is the dip, the break.
Right.
But there's an entirely different marching band in the background playing over it. The host galaxy's blue light is washing out the silence.
That is exactly what is happening. The blue light from the host galaxy is filling in the dip. And while seeing a host galaxy at this scale isn't typical, it is entirely consistent with the dense gas cocoon model.
Because the black hole star model actually expects this excess blue light to be attributed to the stars in the host galaxy.
Exactly. So with the Balmer break explained, the puzzle of Glimpse 17775 was totally complete. Every anomalous line made sense.
Okay, so bringing this all back to the beginning. What does this single solved puzzle mean for the crisis of the broken universe we discussed at the start, the 2022 panic?
Well, it means we can breathe a sigh of relief. Remember, the fear was that galaxies had grown impossibly large, impossibly fast.
Right, requiring billions of old stars to generate that much light.
But the BH star scenario elegantly solves this. The broad emission lines we see don't require impossibly high black hole masses, nor do they require billions of impossibly old stars.
The team proved that Glimpse 17775 actually fits perfectly into the existing framework of the universe's evolutionary history.
Yes. Vasily Kokorev actually said, "Everything fits, nothing is broken," and I think that makes the puzzle that is our universe even better.
So just to clarify, the universe wasn't breaking the rules of physics, we were just misinterpreting the flashlight.
Exactly.
We thought we were seeing a stadium floodlight powered by 1,000,000 stars, but it was actually a tightly focused, incredibly hungry black hole glowing through a cosmic fog.
If we connect this to the bigger picture, it shows that science is working exactly as it should. A terrifying anomaly was observed, it was tested, and eventually elegantly explained by combining multiple disciplines and instruments.
It's an incredible journey. I mean, going from a terrifying cosmic anomaly 600 million years after the Big Bang to getting a heavily magnified lucky break with gravitational lensing.
Working through a literal forest of iron signatures.
And finally realizing it's a hidden supermassive black hole. It's just amazing. But what's next? Because this is just one object, right?
It is. The astronomical community is incredibly excited for the future. The next goal is to dive even deeper and definitively prove what is powering the central engines of a much larger sample of these little red dots.
Because while the BH star model is the leading theory, there are other interesting theories being proposed too, right?
There are. And with more observation time, the community might actually have the final definitive answer in just a year or two.
A year or two? That is incredibly fast for astrophysics.
It's an exciting time to be looking up.
It really is. And you know, I want to leave you listening to this with a new idea to ponder that really builds on this bizarre reality.
Oh, absolutely.
Because if our universe's history is populated by these incredibly energetic, gas-choked, supermassive black holes just masquerading as innocent stars, How many other basic assumptions about the empty spaces in our night sky are actually just masks hiding unimaginable cosmic engines?
It really makes you question what you're looking at.
It does. Next time you step outside on a clear night, look up past the familiar constellations and just wonder, what else is hiding behind the fog?